Okay, great. Okay, today's plan is to do some problems. As you can see, the first one is exactly the homework problem you have. I think it's good to work out some problems. I prepared 3 problems. The second one and the last one are previous exam problems. So this one is homework. Since it's a homework problem, I think most of you guys already think about it. So let's just do it together. Yeah. So okay, we have electron gas outside metal. So basically, we have some metal. Let's assume it's on the right hand side, and there's some electron gas. Okay, so they are in equilibrium at temperature T. So the work function of the metal is W. And here explains what is the work function, basically assuming this is the Fermi energy. Assume this is a ground state, like the bottom of the band, then it's epsilon equals 0. So energy equals 0. This work function is the energy that we need to pay to take an electron from the metal to the outward, right? Let's draw a spectrum for the free electrons, and this is the P equal to 0. So basically, this is the energy you need to pay to kind of put an electron from the metal to the P equal to 0 state. And in this situation, you need to find the number of particles, sorry, number of electrons per unit volume outside the metal when the temperature is much lower compared with this work function, right? Okay, so what's the right? This is the question. I mean, in the equilibrium, we know the chemical must be the same across the system, right? So we only need to work out the chemical potential outside and the chemical potential inside the metal. By the way, feel free to stop me whenever you want. Okay, so inside the chemical potential is, if we choose this bottom of the band as 0 energy point, then the chemical potential inside is nothing but the Fermi energy. I mean, approximately. Outside this metal, I mean, for in a free electron gas, we know there is a formula. I mean, we derived it before, right? What's that? I think it's kBT log something. Yeah, kBT log n and lambda cubed. N is the particle density. Lambda is the double is thermal wavelength, right? There is expression, I think it's H divided by some m kBT pi or pi 2 pi or something like that. Yeah, 2 pi m kBT, right? However, this is not the final result, because when we derive this result, we always regard P equal to 0 state as the 0 energy point, right? Now the 0 energy point is this band, the bottom of the band, meaning that we need to add this energy, by the way. This is W plus EF. That's the that's the chemical potential for the electrons outside. I mean, once you have these results, you just equal them. Plus W plus F equal to EF. And this chemical potential cancel out for the metal. And the KBT log. By the way, here we actually assume the electron gas is dilute, so we can treat them as a classical gas. This is reasonable because my temperature is very low, and we know that at low temperature, electrons want to stay in the low energy state, right? And the metal compared with the electron outside, like the states outside, has lower energy, so it's reasonable to assume the electron gas outside is dilute. As you can see, I mean, to be consistent, eventually we should get a result that the density of the electron, this N, outside the metal should be much smaller than 1 at this limit. If we get some opposite results, that means something goes wrong, right? W log N will be equal to some algebra, take an exponential T lambda Q, oops. What we want is the N, is the density. So it's like that. Yeah, this is the final answer. And remember this lambda equal to H. I mean, there's some prefactors I really don't. And here is T to the -1/2, right? Meaning that this is T. Yeah, correct me if I made some mistake. Something like that. As you can see, since we assume the temperature is much smaller compared with the work function, meaning that, I mean, this is much smaller than 1. And this is self-consistent with our assumption. The electron gas is dilute. And we can treat it as classical particles, gas. Yeah. So any question about this problem? Yeah, this type of question is very typical, right? It's often appears in exam. By the way, here we made an argument that if we shift the 0-point energy, we would add some constant value to the chemical potential, right? This is a very heuristic argument. We can make it rigorous. I mean, the proof is very simple, but I think at least we need to do it at least once. So basically, now the Hamiltonian outside for the electron gas outside the metal is given by p squared divided by 2m, right? It's a free gas plus some constant potential, meaning that we're shifting the 0-point energy. In this situation, is nothing but W plus EF, right? So in our case, this phi, by the way, the phi is a constant. It's nothing but W plus. So now we want to prove that the chemical potential for the electron gas outside equal to the original one. This one is derived from the Hamiltonian with only p squared over 2m term plus 5. That's what we want to prove, right? Is it clear, like this, the question I'm trying to solve here? Okay, so I mean, just the standard thing, right? We did it many times. Let's work in the canonical ensemble. You can also work in the grand canonical ensemble, but it doesn't matter, you will get the same results. Okay. Canonical ensemble. So partition function is nothing but the integral over all the possible states. And the beta epsilon, summing over all the particles. Plus psi. Let me add another page. Okay, so I mean, we always want to connect this new problem to our previous problems that we are familiar with. So we recognize that this term can be written as product of this term times this term, right? Because phi is a constant, and the n summing the summing is is from 1 to n, so it's n, and this first term is nothing but the the partition function for the electron gas with Hamiltonian p squared divided by 2m. That's the previous Hamiltonian. This is the previous partition function we worked out.
I had a quick question here. So this is for the gas outside of metal, right?
Exactly, yes.
Okay. That's why it's not distinguishable, right?
Right.
Okay.
Yeah, to me, whenever you have some continuous degrees freedom, it's usually is not distinguishable because they mix with each other. If you have some finite energy levels, meaning that somehow it's confined, because whenever only when you get confined, you have some discrete energy levels, right? In that situation, I would say it's distinguishable. For example, for the two energy level systems, and in that situation, the translation degrees freedom along different dimensions, along different directions are frozen, and that's why the spectrum is kind of discrete and there's no continuous spectrum. Yeah, thanks for asking. And once we have the partition function, the standard procedure, we know what is the free energy, right? Not V. So there's a T. Log Z naught plus log expansion minus B. So minus KBT log Z naught plus, so this is minus KBT times minus beta n phi. Okay, so I just copy the first term. Oops. It says my internet is not good, but yeah, here's just some trivial steps. Minus sign cancel with this minus sign, and this KBT cancel with this beta. So we're left with N 5. And on the other hand, we know dF, I mean, this is just the energy conservation, dF equal to minus S dt minus P dV plus mu dm. This tells us mu equal to partial F partial N. And the first term will give us the standard N lambda cube, the standard chemical potential we calculated before. The second term will give us the phi, which is the constant. This is just a sanity check. I mean, it's always good to have some simple calculation to check your kind of intuition. Right? Any questions about this first program? Okay, I guess you already worked it out, right? It's a homework problem. Yeah, so let's look at the second problem. This problem is one of the final exam problem when I was taking the class with Zuki. You can, and maybe I can give you like about 6 minutes. It's a very short program. Just think about it. You don't need to do any calculation. You just think if this is a exam problem, how would you approach this? And yeah, then we can go through it together. Also, let me know if there's anything unclear.
So I don't quite understand why it's free to move in 2D. Is it like, is the surface 1D?
It's like, okay, thanks for asking. The system is like this. We have some free particles outside, and particles can be kind of absorbed on the surface, and on the surface is a 2D is a 2D plane, and it's free to move on this surface. This basically a 3D system attached with the 2D system. And
okay, so whenever helium is in gas, it can move in 3D. Okay.
Yeah.
So I guess it's one of those detailed balance problems.
Actually, in this case, you don't need the detailed balance. It's quite similar to our previous problem. There's an energy difference between those two systems, and you only need to write down the chemical potential for both systems and equal them. You get the equation. That's basically what you need. Yeah, for the last problem I'm going to talk about, that you need detailed balance. Yeah, I guess everyone already think about it. Maybe we can just do it. It's a very quick problem. Okay, so basically, like what I said, we have two systems. One is the 3D free electron. Sorry, in this case is a helium, but doesn't matter, particle gas. And in 2D, in the surface, on the surface, we have some also free particles. Let's draw in this way, like similar to what I draw here. Let's draw. This is a 2D. Imagine like yeah, it can move, and this is the bulk. And outside there's some gas, right? Some particles moving around. So for the particles on the surface, we have a spectrum, and for the gas, for the particles moving outside, we also have an electron, but there's a difference between those two, which is given by the work function, which is a phi in this situation. And for the 2D, the chemical potential is given by, the same procedure as what we did before. The only difference is now it's lambda square instead of lambda cube, because when you do the integral, it's p square, something like that, right? Originally there are px, py, pz, 3 components, but now we have only 2 components, and we would get that lambda square instead of a lambda cube, and equal to the chemical potential outside. In this situation, outside chemical potential is kBt log lambda, the density times lambda cube plus 5. And okay, so to determine the final quantity we need to calculate is the particle density at equilibrium on the surface, right? So basically we need to calculate this N2D. The quantities we know the pressure and the temperature outside versus the temperature is versus the temperature of the surface. We know P and T according to PV equal to N kBT, right? We know this gave us N divided by V equal to P divided by kBT. So this N divided by V equal to the N, so it's the particle density for the electron, for the particles outside. So basically we know this guy, we need to calculate this guy. And of course we know the lambda. Lambda is only a function of time, temperature and the mass of the particle. Let's add another page. Okay, so let's write down the equation. Some manipulation, right? We move this term to the right hand side. We get kBt log N2D divided by N3D. Lambda, I guess, equal to 5. And so log, so N2D 3D lambda equal to the exponential of 5 divided by kBt. So N2D equal to N3D lambda exponential of 5 kBt. And this guy is what we calculated before, is P divided by kBt. Yeah, that's basically how we solve this problem. In the same spirit of how we solve the first one, so this problem. this homework problem. You can also come up with your own problem like this. So any question about this one? Yeah, I guess if you understand the first problem, the second problem is very natural. Okay, so let's look at the last one. The last one is a little bit longer. I need to, yeah. Maybe give you about like, I don't know, maybe 5 minutes to read through this program. It's a very interesting program, I think. Also, let me know if there's anything unclear. Okay, maybe I can explain the system to you guys. So basically we have two-dimensional systems. So one is the lower table. So it's another color. Another one is the higher table, the upper one, the upper table. And the difference of the height is h. And they are all two-dimensional systems. Of course, if okay, so there is a slot with A, so particles can exchange, like the particles of those two systems can exchange, and eventually it can reach the thermodynamic equilibrium, right? Of course, if A is 0, meaning that those two systems are separate, like they are not interacting with each other. Yeah, that's not interesting. So here we consider there's a slot with A, and they can exchange particles. Eventually, they will reach the equilibrium, and all the problems A, B, C asking some properties of the system. Yeah, that's basically the system. Part A is very similar to what we did before. Basically, there's a constant potential difference between those two systems, and we can write down equation for the chemical potential for those two systems. And part B, we need to calculate the rate like of particles going from one system to another. Let's call this system 1, the right table 2. So we calculate the rate that particles going from 1 to 2 and versus the rate of particles going to 2 to 1. And the part C basically ask us from the detailed balance, we will get the same results with what we have in part A. Detailed balance means the two processes are the same, right? The rate are the same. And that's basically the questions asking. Is it clear? Like what's the problem asking for and what's the problem? Cool, thanks. Yeah, okay. Yeah, I mean, whenever you want to solve a problem, first thing you need to define the problem, right? You need to define it clearly and understand it clearly. Then you can start to solve it. So for the part A, like what I said, what we did before, right? We write down the chemical potential for the part 1, for the one part, which is kBT log and lambda square, right? By the way, it's good to remember this expression. It's not that complicated. It's just kBT log and lambda, like to the power. The power is the dimension of the system, right? Of course, you can also derive it, but it's good to remember. The chemical potential of the part 2 is similarly is given by kBT log and 2 lambda square. By the way, two lambdas are the same because they're the same type of particles and versus the temperature the same across the whole system, right? And plus mg, there's a height difference, which will give us this potential. So let's equal them. We get an equation. What's this? Let's just move this term to the right, sorry, to the left. kBT log n1 divided by n2, right? This lambda square cancel out. mgh. So this is n1 divided by n2 equal to exponential kBT mgh. Yeah, of course, this result makes sense. Yeah, when your temperature goes to 0, all the particles will stay in the part 1, right? Because when temperature goes to 0, this guy would goes to this exponential term would go to infinity because exponential infinity for infinity, meaning that n1 is infinity, or n2 is 0. And when temperature goes to infinity, meaning that there will be no difference between those two tables, right? Because the thermal fluctuation is so large that it can ignore the height difference. Yeah. when t goes to infinity, you can say n1 divided by n2 equal to 1. So they're the same. Yeah, it's always good to kind of check various limits, physical limits. Right. This part 1, part A. Any question about part A? Yeah, I think part A should be clear. Let's look at part B. So for the part B, we have two systems, right? Part 1 and 2. Some particles, the coordinate is, I believe, is x, y, and z. So particles moving around, and some particles will go through this slot, and from 1 to 2, or from 2 to 1. We need to calculate the rate from 1 to 2 and the rate from 2 to 1. So in this situation, we need to invoke the so-called Maxwell distribution of the velocity. PV, because it's a two-dimensional system. By the way, the definition of this guy, the physical meaning of this guy is the number of particles with velocity Vx, Vy to Vx plus dVx, Vy plus dVy divided by the total number of particles. And this guy, if you didn't remember the expression, but you should know it's proportional to minus beta and the kinetic energy, right? The kinetic energy is mv squared. So it should be some kBt, something like that. There are some prefactors, and you can determine the prefactor by kind of impose the normalization constraint, right? This integral should integrate to 1. So you can determine it, which is m divided by 2 pi kBt in 2 dimensions. Right? Okay, so then the number of particles per area with velocity Vx, Vy to Vx plus dVx plus, okay, let's write it down. Number of particles per area with velocity Vx, Vy to Vx plus dVx, Vy plus dVy equal to n. N is the number of particles, sorry, the density of the particles of the system. PV, dVx, dVy, right? So for the region 1, this is n1. For the region 2 is n2. I mean, the dimension of this quantity is 1 over L squared, 1 over length squared. Right? This is a dimensionless quantity. Of course, it's the number divided by number. So it's dimensionless. And this guy is the number divided by the area. So it's area, 1 over area. Right? Now we need to calculate the rate. Let's first consider the rate from 1 to 2. Okay, so what's this guy is? First, of course, we know we need times Vx. Vx is the velocity in the x direction, right? And also we need to times the width of the slot. It's very intuitive, right? If we get another A or another velocity Vx, then we should have another rate from 1 to 2. And if you worry about maybe there's some other factors, you can check the dimension. This guy has dimension 1 over L squared. L is the length, and okay, this guy has dimension L over T. T is the time. This guy has a dimension L. So you can say L times L divided by T times 1 over L squared equal to 1 over T, which is a rate. Right? So there, this is the expression. Now we only need to integrate over the dvx and dvy. Is there any question about this expression? Yeah, whenever you are not sure about the physical meaning, you can always look at the dimension. It can tell you some basic information about what the quantity describing. And the dyx and dvy, it's a vx and pv. Now, for the vy, we have no constraint, right? Vy is the velocity in the y direction. It really doesn't matter. So it's minus infinity to plus infinity. But for the Vx, we have a constraint. Of course, first we know Vx must be positive, meaning that the particles must be moving in to the right direction, right? If it's moving in this direction, you will never pass this slot. And another constraint is, remember, there is a energy difference. There is a height. Basically, there to passing from 1 to 2, region 1 to region 2, the energy you need to pay is mgh, meaning that there is a lower bound for your Vx, right? Basically, your kinetic energy along the x direction should be larger than the energy you need to pay. Sorry, Vx equals m cancel out square. So this is the minimum energy we need to have for the particle to be able to passing through this. Questions?
So with some more problem in class, yeah. So we did a similar problem in class, and if for the lower bound for V, we also included, it needs to be like basically close enough so it contacts with the boundary.
Yeah, so here,
right? So there was like a time-dependent term. I forgot what it was.
Time-dependent term.
You know what I mean? Like, if it's
yeah, I know what I mean. You mean
like if it's 10 meters away?
Yeah. I know what I mean.
It better move fast to get to the boundary.
Yeah.
And if it's right at the boundary, then it's not. Yeah. Mm-hmm.
Yeah, I mean, I think in that situation where you are calculating the flux, right, or what? Basically, the number of particles that's going through some region for some time, right?
Yeah, we had like.
Oops, I think my connection is really bad.
Yes, sorry.
Okay, sorry about that.
So,
yeah.
I guess I see that there is a little bit of difference, but I have another question.
Mm-hmm.
how does it, you're calculating that it has velocity only in x, y, but you need to jump in z direction, right, to pass over the boundary.
Yes. Yeah. Well, what's your question? I actually cannot hear very clearly. Or you can type in the chat, I think. Yeah, my connection is always bad at the end of the discussion. I don't know why. By the way, I think the time is up. So if you want to go, you're free to go. Oh yeah, that's because there's a ramp. Oops. Thanks for asking. Oh, what's going on? So basically, there's a the system is like this. Yeah, yeah. Otherwise, there's no way for the particle to jump to to the second floor, right? Yeah, that's true. Yeah, thanks for asking. Yeah, it's very unclear in the picture, but there's there's a ramp, so the particle can climb from the first floor to the second floor. Yeah, basically this is the solution. Sorry, this is the expression, and you plug in. This is just a Gaussian integral you need to do, and you can do it by yourself. And I can, yeah, there is. I think the particles just go through from this region 1 to region 2 smoothly. There's no crazy stuff. Okay, let me write down the answer. So it's the N1, of course, is proportional to the number of the density of the particles. N1 A squared 2 KBT 2 pi m summation minus m to h. Right. R2 to R1, similar expression. The only difference is the integral. So now for the Vy, similarly, is from minus infinity to plus infinity. For the Vx, there's no constraint as long as the motion, the direction of the motion is to the right, to the left. So basically means from minus infinity to 0. And the similar expression. This is N1, A, Vx, N2. And you can work out this. It's nothing but N2A. Yeah, you can say they have the same factor here. We really don't care. What we care is this exponential factor. So if we impose the detailed balance, 1 to 2 and 2 to 1, they're the same, then we obtain the same result as what we obtained in the first part. That's basically like 2 approaches to solve this problem. Yeah, I think this is a very nice problem because it kind of combines a lot of ingredients we learned in STEM Math, right? Great, that's all I want to say. Yeah, thanks for asking questions. I guess see you next
Thank you,
week.
this was helpful.
Yeah, cool. Yeah. See you guys next week, I think. Bye.